In this video, I'm going to show you how to solve an interesting IV infusion rate calculation question which involves understanding milliequivalents and percentage concentrations. And if you watch this video until the end, I'm going to show you how you can use artificial intelligence to solve this question in seconds. Hello, this is Dr. Danquah. And if this is your first time here and you like to learn pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Now, if you want to take your academic performance to the next level, then be sure to check out these two softwares which we created. The first one is Bevinzey, which is the #1 AI-powered learning platform. And I'm going to be using Bevinzey at the end of this video to show you how to solve this particular question. The other application is Study Socials, which is the student's quintessential productivity companion. So I'm going to put the links to those two softwares in the description and you can go check it out for yourself. But let's get right to it. The question says, the clinical pharmacist in the pediatric ICU is asked to determine what rate to run a child's IV at. The IV contains 9 milliliters of 39.2% potassium acetate in normal saline to prepare a 1 liter bag. The prescriber wants the child to receive 2.5 milliequivalents per hour. What rate in milliliters per hour would provide the desired milliequivalents per hour of potassium acetate? Answer must be numeric, no units or commas, round the final answer to the nearest whole number. So let me start off by breaking the question down. The ultimate goal here is to determine the flow rate in milliliters per hour. You've been given a rate. Now this rate is in milliequivalents per hour. And also you've been given some concentration here. So you have 39.2%. So now let me quickly outline a few steps that we'll be following in order to get to the solution. The first step will be to determine the amount in milliequivalents of potassium acetate that is present in the 1 liter bag. That's the first thing we're going to do. And then we're going to use dimensional analysis to solve this question to get the flow rate in milliliters per hour. So let's start off with the first step. So to determine the milliequivalents, we first need to recall that milliequivalents is equal to the quantity of the substance in milligrams divided by the molecular weight times the valence. So we need to determine the valence here, and we're going to use the formula for potassium acetate. So potassium acetate is essentially CH3, CO2, and then the potassium. And when you put this in an aqueous environment, it's going to dissociate into the potassium cation and then the acetate anion. So now if you need a more extensive review on milliequivalents calculation, I'm going to put a few links in the description and also link it in the cards. But here, what we want to do is to determine the valence. And the way you do that is to take the absolute value of the charge that is either on the cation or on the anion. So the absolute charge of +1 is going to be 1 if you're using the cation, and if you're using the anion, the absolute of -1 is also going to be 1. And so the valence is going to be 1. Now, the next piece that we need to use the milliequivalent equation is to find the quantity of the substance in milligrams. And that information is not given to us explicitly in the question, but we're going to make use of the percentage concentration and then the volume that was taken to determine the actual amount of potassium acetate that will be present in the 1 liter bag. Because as the question implies, you're going to take 9 milliliters of this solution, which has a concentration of 39.2% potassium acetate, and then you're going to put the 9 milliliters in the 1 liter bag, which means that all of the potassium acetate in this 9 milliliter volume is going to be present in the 1 liter bag. So let's proceed by doing that. For the 39.2%, you want to recall from percentage concentrations that it implies we have 39.2 grams of potassium acetate in every 100 milliliter of solution. And our goal is to determine how many grams and ultimately milligrams will be present in 9 milliliters of the solution. So we go ahead and solve for x, which is the unknown. X is going to be equal to 39.2 grams times 9 milliliters divided by 100 milliliters. The milliliters cancels out and you end up with 3.528 grams of potassium acetate. But notice we need to have that value in milligrams. So we're going to do a quick conversion. So 3.528 grams. You multiply this by the conversion factor. 1 gram is 1,000 milligrams. The grams cancel out and you end up with 35.28 milligrams. So now the next thing that we need is the molecular weight, because it's not given to us directly, but we have the molecular weight of potassium and of the acetate. So to find the molecular weight of potassium acetate, we're going to add these two numbers together. And so molecular weight is going to be equal to 39 plus 59, and that's going to be equal to 98, and that's your molecular weight. So now we can substitute the valence, the quantity in milligrams, and the molecular weight into the milliequivalence equation. And what that would look like is you have milliequivalence is going to be equal to 3528, which is the weight of the substance in milligrams that we calculated here, divided by the molecular weight, which is 98, times the valence, which is 1, and that is going to be equal to 36. Now, once again, what this means is in this 9 milliliter volume, it contains 36 milliequivalents of potassium acetate. And this 36 milliequivalents will now be present in the 1 liter bag because you added the 9 milliliters to the 1 liter bag. Now, to be more precise, what you're going to be giving the patient is a 1 liter bag which contains 9 milliliters of the 39.2% solution, which implies that this 1 liter bag contains 36 milliequivalents of potassium acetate. So we can now proceed to the next step, which will involve using dimension analysis, and we are going to take the 2.5 milliequivalents per hour, and we're going to multiply this by the volume that we have in milliliters. So we have 1 liter, but 1 liter is 1,000 milliliters. So I'm going to put 1,000 milliliters here. And this 1,000 milliliters contains 36 milliequivalents of potassium acetate. So based on dimension analysis, the milliequivalents in the numerator will cancel out the milliequivalents in the denominator. Then you're going to multiply all the terms in the numerator and divide it by all the terms in the denominator, which implies I'm going to have 2.5 times 1,000 milliliters divided by 36 hours. And this is going to be equal to 69.44. But notice that the question says round to the nearest whole number, do not include units. And so the answer is going to be equal to 69. Now let's take a look how you can solve this question in basically seconds using artificial intelligence. So go to Bevinzey.com, and then once you are logged in, click on Services, and then the module that you want to pick is the Chat Bevinzey. So click on Chat Bevinzey, and just want to copy and paste the question in there. So I'm going to do exactly that. Click on the arrow, and then just let Bevinzey do its own thing. And there you have it. In a few seconds, you have the answer, and the answer is exactly the same as what we got when we did the step-by-step in the earlier part of the video. So just for thoroughness, let's quickly go through the process that the AI used. So in the first step, it decided to calculate the amount of potassium acetate in grams in the solution, which is exactly similar to what we did in the earlier stages of the video. But then in step 2, it decided to go through first principle. So instead of using the equation, it went through first principle. So determined the moles and then converted the moles of potassium acetate to mEq from first principle, and then determined the concentration of potassium in mEq in the 1 liter bag. And then in the fifth step, it determined the flow rate based on the 2.5 milliequivalents per hour. It ends up with 69.44, and it understands to round to the nearest whole number from the question, and so it ends up with 69, just like we got in the earlier part of the video. So I hope you found this video tutorial useful. If you did, be sure to like it and share it. And if you have any questions, just leave them in the comments and I'll get to them as soon as I see them. If you'd like to learn more pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.